Hey guys, this is Joseph Amante. I was going to be lecturing with you this Tuesday, November 10th, but I have another arrangement. I will be out in my field site working, so you guys just get some YouTube video so you can stay inside. It's supposed to be maybe wet and rainy. Little background. My name is Joseph Amante. I just graduated with my master's degree and I work for the Virginia Center for Coal and Energy Research here at Virginia Tech. I do a lot of work in sequestration, CO2 sequestration, which John might be talking about here in the future. But today we're going to be talking about two things: hydrogen, electricity, energy, nuclear energy. But before we begin, I just want to break this down for you. So each of these videos is going to be around 10 minutes, because that's all of my free software will allow. We'll try to break it up, go as quickly as we can. We're not going to worry about the group discussions at the end. But just some things to think about and maybe test questions here and there. So let's get started. But before we get started, let's take a step back and think about where our energy comes from at Virginia Tech. So if you're like me and live out in Ellet, you obviously aren't powered by the Virginia Tech power station because you get an Appalachian power bill every month. But if you're on campus, you might take that for granted, and you're using your computer, so obviously you're using electricity. But where does that power come from? A lot of people know is we have a coal-fired power plant on campus. Well, it's not just a coal-fired power plant. It does coal, natural gas, and liquid petroleum. It has boilers for all three. So it's kind of weird that you see a power plant in the middle of the city in America. It's fairly more common in Europe, and we're going to talk about some of the things that make our power plant really kick butt. It is one of the most efficient power plants on the East Coast for a couple reasons. So the Virginia Tech power plant is a steam power plant. Most power generating plants heat water to produce steam that turn a turbine. So the plant contains 5 boilers that superheat the steam to around 820 degrees Fahrenheit. It produces around 6,000 kilowatts at any given time. Gigawatts. That was Back to the Future. So this power plant is pretty cool for a couple of reasons. So all of that steam that it produces at 825 degrees normally gets vented. So if you think about a nuclear cooling tower, you see all this smoke billowing out. Well, it's not smoke, it's technically steam, or the vapor in the air. So what does Virginia Tech do with that? Well, they use it to heat dorm buildings. Your heating in your dorms is caused by this power plant. Heat hot water for cooking or cleaning, or showers, or autoclaves. So we recycle pretty much 100% of that energy. So anytime we take an energy loss, we use it for something else. So the other cool thing is that the system is almost 100 years old, okay, and we've been upgrading it here and there. Back 50 years ago, we weren't concerned about some of the toxic particulate matter, but now we filter it out. And like I said, most of the byproducts are used for some sort of energy generation, energy loss, heat, cleaning. We actually use the water that's recycled back to spray on the roads before it snows. So this is just a really long slide. I'm just trying to reiterate why this power plant is so good. We get most of our electricity for campus off this, but at the rate we're growing, we probably won't be able to sustain it. Virginia Tech also sells their excess power right now to various places on the grid. So Virginia Tech, compared to other power plants in the area, it's very similar to a commercial power plant, but it's in the middle of a city, so you can use it to do things like heat homes or warm water and not have crazy transmission costs for line. I don't know if John has talked about energy transmission and how it crosses the country and how we have different sine waves and you have to match them up. But it's a district cogeneration, and if you notice, it says potentially very efficient. It is actually very efficient. Sierra Club in 2009 actually praised this power plant, and if anybody knows, Sierra Club is like a more not crazy Greenpeace. It's an environmental organization. They actually applauded our power plant with its efficiency and recycling use. So, okay, let's get started. So we're going to talk about hydrogen, the carbon-free fuel. So hydrogen's a pretty cool substance. What you do is you burn hydrogen in the presence of oxygen, and you're left with two byproducts. You're left with heat and water. Okay, so we're 5 minutes in. I got another 5 minutes in this video. I don't know if I can get through all this stuff, but we'll see how far we can get. So hydrogen is a carbon-free fuel, but we have to talk about how we get the hydrogen, because that might not be carbon fuel, carbon-free. So same thing with solar panels. People say solar panels are green. Yes, they are, but they require a lot of rare earth elements, which is not the best for the environment, mining them, refining them, shipping them, things like that. So we got to talk about how to generate hydrogen in large enough quantities. So to generate hydrogen in significant quantities, the best way to do it is to break apart water. So if you look back here, we get water as an end product of burning hydrogen. So we have to go backwards in this reaction. So it takes a lot of energy to go in the reverse direction. So the conversion of energy from one form to another always results in loss of energy. This is a law of thermodynamics. Everything you do results in a loss. There's never really like a great way to do this. There's some better ways to do this, but another thing to think about is the electricity required for it to go backwards may generate carbon dioxide, so it's maybe not be carbon neutral. Okay, so the other problem is to break these bonds, you have to do over voltages. So you have to supply enough energy to break the bond and break it. Not break it a little bit and then it reforms. So it requires a high over voltage, and then it's not very energy efficient. So hydrogen can also be stripped down from fossil fuels like coal or natural gas. I mean, technically it's possible to make jet fuel out of coal. But you do have carbon waste, and there's some refining processes that you have to go through. So this is just the full electrolysis reaction. It's a two-part reaction, and John here in this example has kind of broken it down for you. So water to get oxygen and hydrogen, and then it's here again in the electron balance form. If you go through this, all it is you end up with water, which you break down. Water, which you break down. You end up with 2 hydrogen, and then the oxygen as both of these are a gas. So electrolysis in water, you can do this with a peanut butter jar and a battery if you want. I would not suggest it. Hydrogen is, again, explosive. So what you do is you basically have an electrical input that you have into a water with 2 various cathodes and an anode. I did that backwards. So what you do is you supply this voltage from a battery into this water, and what happens is you get hydrogen bubbles on one end and oxygen bubbles on the other, and you have to have a way to separate them. So oxygen would be over here in this tank, and then the hydrogen would be over here, right, in theory. And then all it takes is the energy that you require to put into it. But when we're going to go over here in various ways to make hydrogen, and none of them are very energy efficient. Okay, so here we go. Here is one of them. Let me get my notes real quick. I'm going to pop out of this. So this is hydrogen from wind. Let me zoom in a little bit more. So hydrogen from wind, net loss is around 1,500 BTUs of energy. So if we get electricity from the wind, 76,000 BTUs, or electricity from the grid, I'm just doing electricity from wind here, not from the grid. You have energy losses due to electrolysis, producing the hydrogen gas, delivery of it to wherever your compression pipeline is, energy used for delivery operations, so powering however you deliver it. You have energy losses just from heat, cooling, friction, things like that, and then you finally get your net gain of hydrogen gas used as something. So 116,000. So technically you put in 76, but you have all these other energy losses, so your net loss is around 15. If you don't count this energy from the grid, then it's around 100,000. Okay, same thing with biomass. Now we're at 200,000 BTUs lost. 200,000 BTUs lost. So we have biomass production. You get 2 pounds of CO2 equivalent from just rotting and things like that. You have a lot of energy going in from biomass for a gasifier, reformer, water steam system. You have to separate the high and low temperature water into a shift reactor, and then you have to put it to pipeline, and you have electricity, energy losses, gas finally. This is not very efficient, but biomass is something that we deal with all the time. I mean, when you throw away a banana peel, that's technically biomass. It's bio, you can burn it. wood chips from sawmills are technically biomass. So, this may seem like a crazy number, but when we talk about biomass, if you let things rot how they are, they do